Get into this problem that is actually two number theory problems, homework problems from Charles Vanden's textbook. I want to talk about what we mean by number theoretic congruence, and I'm going to use capital A, capital B. A is congruent. Notice this is triple bar, and it's a lot like equality in a number theoretic sense. A is congruent to B, and I'll just use mod K here. Everything inside's an integer. Okay, this is equivalent, and I'll just use the arrow like this in a definition sense. A minus B, relate it back to equality, is some multiple of K. Okay, so I'll write that as just MK. Now notice this could be rewritten just by taking B to the other side. A would be equal to B plus some multiple of K. So that's what we mean by the triple bar congruence. And again, it enjoys many of the same properties as equality in number theory. And so you get an equation. It kind of converts division into equality in a certain way. Okay. Now, again, this is two problems from Charles Vanden's number theory book. It's 22 and 23 combined, and I worded it slightly differently. Hopefully, I kept the intent of the excellent number theory author. Now, so we're trying to prove this result right here, which is actually related to perfect numbers, and I'll try to speak about that a little bit at the end of the video. But we're trying to show this result, okay, for all positive integers. That's what natural numbers are. They're positive integers. Now, notice based on this definition right here, this can be restated equivalently in this equality format, where K at this point is some unknown integer, all right? So this statement right here is absolutely equivalent to this statement right here. Okay, now let's move along. And then this statement, if you divide through by, you get this over this is equal to K, right? So it's all written down. It's no need for me to repeat it, all right? Now, at this point, it's easy to get stuck on what you're trying to do right here, but you may notice that this looks a little like the formula for a finite geometric series. I know that's a little bit of a stretch and a leap of faith, but this looks like the result for the sum of a finite geometric series. Okay, so and here it is. We have this right here. Notice that this part right here, the right-hand side here, does faintly resemble this. Okay. Now notice this is that A is called the common ratio, and R is the number of terms. And notice R is the number of terms because you have A to the first here. You have 1 as a term, so that all adds up to R, right? So there's R terms, and so it's kind of easy to remember this result, and it's not hard to prove it. Okay, now again, we're trying to find a K that will make this valid. Okay, so and again, this is just following your nose. The obvious assignments, we'll call it that. A is equal to 2 to the m, right? And not so obvious as R is equal to n, but it really is if you just take a look at this term right here. Okay, and again, you're just comparing this object right here on the right-hand side of the sum, which is the sum of a finite geometric series, to this object right here, which is related to the thing we're trying to prove. Okay, now if you move along, I just did all the substitutions for you. Okay, I did all the substitutions for you. Believe it or not, this is exactly the same as this. What's going on here that might be faintly confusing is if you have something like this, we'll call it A raised, I'll just use standard letters here, M, and then parenthetically like this, A raised to the M n. That's what's getting used, and I just didn't write it down. Of course, if you have n copies of m objects, you have m times n copies. So that's A to the mn. So he says this is just the famous multiply rule that all the students memorize but don't understand where it comes from. And they always get it confused with the other one, the addition formula. But again, that's supposed to be an n, folks. And you can see this n minus 1 really would be an exponent to this whole thing. If you look at the substitution, I just went ahead and wrote it as this right-hand side, this product form. You notice this right here is in a product form for this right-hand side for this rule. Okay, but you see that completes what we're trying to do, because remember we're trying to show that this is equal to some K. So this entire underlined left-hand side is our K. And we proved it. Okay, we proved it, so I'll put QED. Quite easily done? No, it's really Latin. Okay, now the deal on this that I wanted to talk about, the way this is connected to perfect numbers. You guys know a perfect number is a number that's the sum. It's a famous study that's been by Gauss for 1600 years. The Chinese, Babylonians have studied these things. But this, you can use this to show this fairly famous number theoretic result. If k is a prime, and that's another video, you guys can just see that it works directly from the statement. If k is prime, this implies that 2 raised to the k minus 1 is also prime. And these are called Mersenne primes, the French guy. 2 to the k minus 1, this is also a prime. And I guess that's if. I don't think, it may not be if and only if. I'm not sure. But I know if k is prime, then 2 to the k minus 1 is prime. And the reason why that's important is perfect numbers have this form, 2 to the k. Now they look alike, but they're not alike. Okay. And then they're in this form, all even perfect numbers, and they think that that's the only kind. It's supposedly an open question that there's only even perfect numbers. Some people still speculate there may be odds, but I think most of the people quoted in the note don't think there's a such thing as an odd number. There's heuristic, probabilistic proofs. You know, it's very, very interesting. It's still an open question, but nobody. I don't think the people they're really. I don't think anybody really believes anymore that there's any odd perfect numbers. But anyway, all even perfect numbers are in this form, provided this part right here is prime. Okay. And that's why this is of interest right here. And again, you can use this result to prove this result. All right. So that's kind of a step towards being right in the middle of some of the of number theory on the perfect number side. But anyway, again, perfect numbers of this form. But all we wanted to prove was this congruence, which we did using finite geometric series. You could prove this by induction, probably. Of course, you probably could. And then there's other ways. There's other approaches, I think. But anyway, there you go. And again, to me, the hardest part of this was recognizing that this quotient was actually the sum of a finite geometric series. It didn't pop. It didn't click at all. I had to sit and look at it for an hour, and I go, oh, you know. But it's you know what I mean. It's funny that it's just the symbols that you're using, and what you're on, and you go. You don't stop and think. But this form right here is exactly this form when you make. It's just that same structure with these assignments. But anyway, I guess that does it. So thanks for viewing, and talk to you next time.